red pen?
Yes, red pen.
Okay, I was gonna say. Is it working?
Okay, I'm gonna take the liberty of borrowing my previous drawn diagram from yesterday that still is like, partially present on the board. Let's remember the situation. In one situation, we had just water molecules. And we were heating up our water to try to boil it. Now, if you want to boil the water, you've got to overcome two things. One, the external pressure from the air, and two, the internal attraction of the particles, of which with water you have both. Water's polar, so you're going to have attraction between particles. Water is also likely in this pot surrounded by air. We're probably on Earth with an atmosphere, so we're going to have to overcome both. So we get it heated up enough, we get those particles moving fast enough, and those particles are going to jump to freedom. And when I say jump to freedom, they're going to be able to do two things. Number one, overcome air pressure, and number two, overcome internal attraction. And boom, they are off, free, and that particle is zooming around as gas. That's what's happening when the water's boiling. It's heating up fast enough, so the particles are moving, vigorous enough to break free from their brethren and break free from the external pressure of the air. Now, if you introduce foreign particles into this solution, you don't just have water anymore, you've got water and some other substance. And this other substance that we were considering was salt. So let's imagine that these blue particles are the salt particles. Again, you heat up your water. And as you heat up your water, the particles are moving more vigorously. And while it may be true that some of the particles can find their way to freedom easily, it is also true that because there are salt particles in our water, some of those particles will have a tougher time getting out. Some of those particles will have a tougher time getting to freedom. And as this guy tries to get to freedom, he may run into a salt particle, so then he may have to either force his way past the salt particle or find a different route. In other words, you're going to have to, because of the salt particles, get those water molecules moving more vigorously for them to break free of their environment. This is what we call boiling point elevation, BPE, boiling point elevation. You can elevate the boiling point of any substance simply by dissolving something in it. And you can actually measure this, and there's a chart in our book. It's not really important to look at it, but there's a chart that lists a constant regarding boiling point elevation for various substances: acetic acid, acetone, benzene, carbon disulfide, carbon tetrachloride, ethanol, ether, naphthalene, phenol, and water. We were talking about water here. We know that water's normal boiling point is 100 degrees C at standard temperatures and pressures, right? But now, we can look at this chart, and this chart tells us that the boiling point of water changes 0.51 degrees Celsius per molar. And now that's a question, what is a molar? Because we've talked about moles, but we haven't talked about molars yet, have we? Yeah, right, teeth, right? That comes to mind. This is, by the way, let me write this out, what this is. This is the boiling point elevation constant for water. 0.51 degrees Celsius per molar. Let's talk about what a molar is. There is a characteristic of all solutions called molarity, Molarity is going to be a measure of how concentrated the solution is. You could imagine you could pour a small amount of salt, or rather dash a small amount of salt into your water, or you could dash a large amount of salt into your water. And how much salt you put into your water will determine the molarity. Here's how molarity is determined. It's moles of solute, that's like your salt. How many moles of salt are you putting into how many liters of solution? It's a very simple measure. So let's think about how we could measure molarity. Moles of solute per liter of solution. Let's just grab a couple examples. I'll start with a very simple one. What if we had 1 liter of solution? And what if we were dropping 2 moles of salt into our water? You could know how many moles of salt that was by weighing it. The periodic table tells you how much a mole weighs. So what if we had 2 moles of salt? Well, run the molarity. Molarity is moles of solute over liters of solution. 2 divided by 1, this is a 2 molar solution. Capital M is also used for molar. Why is it 2 molar? Because there's 2 moles per liter. Anytime you see molar, it's telling you how many moles per liter there are. Another example. This one's going to be a little more mathematically intricate, but so what? What if we had 10 liters of solution? And what if we dropped the same, well actually let's drop more than 2 moles. Let's drop 4 moles of solute in. So you weigh up the salt, you get 4 moles of salt. You can figure out how much a mole weighs by adding up sodium and chlorine's weight off the periodic table. And you drop 4 moles into 10 liters. Well, if you want the molarity, it's moles of solute, in this case would be 4, over liters of solution. If you take 4 divided by 10, that makes 0.4 molar. Compare the 2 solutions that we just, hypothetically put together. One of them is a 2 molar solution, one is a 0.4 molar solution, one of them is more concentrated. You can tell how concentrated based on the molar number. So this guy has 2 moles per liter, whereas this guy only has 0.4 moles per liter. Above, saltier water. Below, less salty water. There's more moles per liter above. That's going to measure your concentration. So when we talk about molarity, what is this a measure of? It's a measure of concentration of a solution. So how concentrated is your solution? You can determine by this molarity number. And here's the interesting thing. For every single number in molarity, for every molar number you increase, you will increase the boiling point by 0.5 degrees Celsius. So you drop 1 mole of salt into 1 liter of water, you have a 1 molar solution, you're going to knock the boiling point up to 100.51 degrees. This solution here, which is a 2 molar solution, this is going to increase the temperature by what? You can actually do the computation there. We have a 2 molar solution, and we know that we do 0.51 degrees Celsius for every molar. The molars will cancel, and you'll see that will increase the boiling point by 1.02 degrees Celsius. This solution at 2 molar has a boiling point of 101.02 degrees Celsius. The boiling point's been elevated. Why? There's particles in the way. There's particles in the way of the water particles trying to escape. And those salt particles or those whatever particles are dissolved that get in the way prevent the water from boiling as easily. So you've got to increase the temperature. In this case, you have to increase the temperature by an additional degree. Why do you throw the salt in the pasta water? Because it's going to increase the boiling point of the water, it's going to cook the noodles faster. What's going to cook the noodles faster, 100 degrees or 101.2? 101.2, that's why you throw the salt in. That's why, especially at elevation, where it's harder to get the water heated up as much because water can escape more easily from less air pressure, it's more common to throw more salt in your water. Why? Elevate the boiling point. Now, let's think in reverse. What if we were trying to cool off particles to where they solidify? We're trying to freeze particles. Let's think in reverse. So we have these particles here's liquid water. And now if you want to freeze it, what's going to have to happen to the particles to go from a liquid to a solid? What's going to have to happen to the particles? When you think of the particles of a liquid versus the particles of a solid, what's a fundamental difference? They're still close to each other, but they're what? Slower moving. As a result, what do the particles look like? Like if I was drawing solid water down here, what am I going to have to be, how am I going to have to draw it to draw a better solid? Yes?
They look like structured.
Structured, more arranged, yes. So, if we're going to freeze our water, we're going to have to get our water to line up next to each other. And to do that, you can slow down the water particles enough to where the particles will start to line up with each other. And when they start to line up with each other, you form the solid. As a result of slowing down, right, things can settle in to their place and just jiggle in place in this tighter, more compact solid. Make sense? Now, what if this liquid that you were trying to freeze had other substances mixed in with it? This is liquid water with solute. Something's been dissolved. Now, as those particles try to solidify, they're going to have to settle next to each other. And the process of getting water molecules to settle next to each other is going to be more challenging as a result of these solute particles getting in the way. Because if I want solid water, what I'm going to have to get is my water particles settled down to where they freeze and form that solid, and then I'm just going to have my solute particles sitting up here separate from them. And as my water particles are trying to slow down and freeze and settle next to each other, they're going to have a harder time with these other particles in the way. Agreed? Easier to get next to each other when there's nothing getting in your way than when there's something getting in your way. So it's going to be harder to freeze this water than it is the pure water. Are we okay with that? So that is also, we called, when we were trying to boil, we said, you put stuff in your water, it's harder for the water to boil. Well, guess what? When you put stuff in your water, it's harder for the water to freeze as well. And this phenomenon, harder to freeze with solute dissolved, this has a word as well, or an acronym I should say, to describe it. It's called FPD. Fort Wayne Police Department, right? No. FPD, freezing point depression. Now the word depression tells you what's going to happen to the freezing point. The freezing point is going to get lower. It's going to be harder to freeze the water. You're going to have to get the water colder in order to freeze it. Because in order for those water molecules to settle next to each other, they're going to have to be moving slow enough to settle next to each other, which is gonna be harder with that stuff dissolved. Now, you can go to tables, scientists have determined these values experimentally to determine how the freezing point of water changes. And there's a constant for that as well. Now, for water, this is the freezing point depression constant for water is this. I'm just reading it right out of the chart. 1.86 degrees Celsius per molar. So that means every mole per liter that you dissolve of solute, you're going to depress the freezing point 1.86 degrees Celsius. So, for example, pure water has a freezing point of 0 degrees Celsius. Here is a 1 molar solution of water. That means I have 1 mole of something dissolved for every liter. 1 mole per liter. This guy is going to have a freezing point of negative 1.86 degrees Celsius. Why? Every molar depresses the freezing point 1.86 degrees Celsius. Every bit of solute you dissolve makes it that much harder for the water to align itself. Now, think of this. What happens in Indiana in the winter to our roads whenever there might be a snow day? What does the city do to help save the roads? They salt it. So you have these big trucks dumping salt out onto the snow, onto the ice. What does the salt do? The salt mixes with the water. And when the salt mixes with the water, it makes the water harder to freeze. It depresses the freezing point. So water normally freezes at 0 degrees Celsius. But now if we throw salt on it, the water will freeze at negative 1.86. Instead of the water freezing at 32 degrees, now the water will freeze at 30 degrees. It's got to be colder for the water to freeze. The water's going to stay liquid longer. And correct me if I'm wrong, when it comes to road conditions, the last thing you want is frozen water. What you want is water that's harder to freeze. Every bit of solute you dissolve, it's harder to freeze. So why does the salt truck throw salt? And then why is there a second salt truck behind it throwing more salt? Because the more molar, the more concentrated your solution. What if you had a 2 molar solution? Now, if it's 1.86 degrees Celsius per molar, here we have 2 molar, that's going to be 2 of those 1.86 degree chunks. That's going to be minus 3.0, math, come on, minus 3.72 degrees Celsius. Even harder to freeze. Why 2 salt trucks? Because 2 salt trucks means twice the salt, and twice the salt means twice as hard to freeze. And that's good. Because if we can depress the freezing point from 32 to 30 to 28, now it's got to get down to 28 degrees for the water to freeze. And that 4 degrees can make all the difference when the low temperature is 28. Throw salt down, we're going to be fine. Now, if the temperature is like negative 20 Fahrenheit, you can throw as much salt down as you want, the water's going to freeze. When it gets super, super cold, well below freezing point of water, you won't even see the salt trucks out there. Because it doesn't matter how much salt you're going to throw down, the water's going to freeze anyways. You're only able to affect the freezing point by 2 degrees Celsius for every molar. But if you're close to 32 degrees, you're going to dump every bit of salt you can. Because you're going to want to make that water as hard to freeze as possible. Because if that water is liquid water, it's just a rainstorm. If that water is frozen water, you have a sheet of ice in the road, and that's treacherous.
Is the salt like a special kind of salt?
Actually, that's a good question. That's a good question. Is this special kind of salt? Normally, no. Normally it's just sodium chloride. Now what happens, think about this for a second, what happens to the sodium chloride whenever you dissolve it? How does the water dissolve the salt? We talked about this yesterday. What does the water do to dissolve the salt specifically? It attacks it, right? So the sodium chloride, when dissolved, dissolves into sodium and chlorine. So what you actually get are 2 particles dissolved for every 1 salt molecule. Because the water, when it attacks it, will actually break apart the chlorine and the sodium. Recall? Normally, we just use salt. I've never driven a salt truck before. I'm talking about we the people. Normally, we the people use salt. I'm using the royal we. Sometimes, and we have special stores of this, calcium chloride. Why would we pour calcium chloride? Well, think, when the water attacks the calcium chloride, every molecule of calcium chloride is going to turn into 3 ions, because you have 1 calcium ion, but 2 chloride ions. So you can actually get more stuff dissolved, because every time you break apart, and you will break apart these, because that's what water does, it's going to attack the calcium chloride. Every time you break apart a molecule of calcium chloride, you're going to get 3 particles for every molecule, versus 2 particles for every molecule. And more particles means lower freezing point. Sometimes the trucks will use calcium chloride in the event that they need to change the freezing point more. Because rather than 2 particles dissolved, they're going to get 3. And that's going to give them more molar bang for buck. That's going to allow them to increase the molarity of the solution more. And if you increase the molarity of the solution more, it's going to be even harder to freeze. Because every molar is 1.86 degrees Celsius. That's about 3.5 degrees Fahrenheit. So you're going to want every particle you can dissolved in that water if you're the city trying to lower the freezing point.
How are the size of the particles affected the boiling? Does that affect the freezing point?
Yeah, so the only thing that affects the freezing point is the molar concentration. We don't care what's dissolved, we just care how many moles per liter. It's interesting that that's the only thing that it matters. It doesn't matter whether it's calcium ions or sodium ions, it just matters that there's ions. And it matters how many ions per liter. Molar comes down to moles per liter. So whenever you look at the snow on the ground, you have liters of water on the road, liters and liters and liters. There's tons of, as the snow falls, I mean, you have inches of water on the road, that's liters of water. You're going to need moles and moles and moles of salt just to cover those liters of water to get up to 1 molar. Because you're going to need 1 mole for every liter. You're going to need 1 mole of salt. Sodium weighs 23 grams, chlorine weighs 35, so 23 plus 35 is 58. You're going to need 58 grams of salt for every liter of water to bring the temperature down that much. So that's why, have you ever seen these big igloo type structures that are on the side of the highway, and you wonder what in the world do they keep in that igloo? The answer, salt. There's like these big, I don't know how to, they're shaped like this, and they'll have like a garage door on them. And they're like on the side of the highway. Maybe you've seen structures like this, these big igloos. And they got a door on it. What do they fill? It's just a giant pile of salt inside. And the salt truck will back into it, and the salt will dump into his back of his truck, and he'll pick up the back of his truck, and he'll drive away, and he'll have a big truck full of salt, and then he'll spray the salt all over the road, and then come back and get more. So if you ever see these big igloos, they're full of salt. Literally salt. Some of the igloos might have calcium chloride when you need that extra punch. But as you can probably guess, calcium chloride is a little bit more expensive. It's harder to run into this salt than it is that salt, and it's going to be a little bit more expensive. But you get 3 particles for every molecule, which is going to give you more dissolved particles, and is going to allow you to depress the freezing point more. That could save lives. That could save lives. Every degree counts when you're hovering around 32 degrees and you don't want the water to freeze. So stuff dissolved in water makes the water harder to boil because there's stuff in the way. It's going to raise the boiling point. It also makes it harder to freeze, so that's gonna depress the freezing point. In other words, it's gonna make the boiling point higher and the freezing point lower. Helpful when you wanna keep the roads free of ice, also helpful if you want to cook your pasta noodles faster. And the salt will actually make the pasta noodles taste better too, so you can add that as an extra reason. In Italy, back in the day, whenever they used to just, when there wasn't running water, like back in ancient Roman times, they just go out to the Mediterranean Sea and scoop up salt water to put their pasta noodles into. Because the salt water would flavor the noodles, and the noodles would taste better, and the noodles would also taste like the sea. So especially if you put like clams or mussels or fish or any kind of seafood, which you commonly be using because you're in Italy and surrounded by water, so most of your protein is fish, you're gonna have like a super sea-ish tasting meal, and that's gonna be pretty delicious. I'm not sure if any there's gotta be Italian eateries who still do that to this day, there's gotta be. But that's how they used to do it back in the day. Before there was running water, just go scoop up a little bit of the Mediterranean Sea, throw your pasta inside. You get the advantage of the salt, it flavors the pasta and it cooks the pasta faster. Why? Raises the boiling point. If you're at elevation, even better, right? Because if you're at elevation, you have less air pressure weighing down, and your water's gonna boil at lower temperatures. That makes it longer, takes it longer to cook. And that would be a hassle. Who wants to wait an extra 2 minutes on their pasta noodles? I want my pasta noodles now, right? Throw the salt in. And remember what a molar is. This is not trivial. In your notes where you have what a molar is. Remember molarity, which is how we measure concentration, is moles of what you dissolve, moles of solute per liters of solution. And the higher the number, the more concentrated. That means more moles per liter. That means more stuff per liter. More stuff means more dissolved, more concentrated. So 2 molar salt water is going to be saltier to the taste, saltier to the effect of making it harder to freeze as well. Does this make sense? Good. That's a big idea. Let's see what time it is. Nope, 8:52. So the bell's going to ring here in just a jitty. That'll be it for today. If anybody ever asks you though, how does throwing salt on the water, or throwing salt on the ground save, traffickers, save motorists, you can always explain it now, which I think is a nice thing to know. Because, if you really think about it, why the salt, right? Is it for traction? Right, that's what I used to think when I was a little kid. I was like, you have like little things on the ground, now you'll be able to like grab the road. No, nothing to do with traction, and maybe it does increase traction, but what it does is it makes the water harder to freeze.